Hey guys, Bobby Thompson back with another video, and in this video we're going to be talking about Graviteehee. And before we get started, let me just say that if uh, if there's a section that doesn't interest you, you can skip it. I've broken this video up into chapters. If you're not familiar with chapters, if you mouse over the bottom of the video, you should see a white bar that's broken up into chunks. If you mouse over one of those chunks, it'll show you the title. You can hop to that title and just watch what you're interested in. I like to start every video with some definitions just to make sure there's no ambiguity of any terms. Some of us haven't been to a science class or in 30 or 40 years, so we'll just go over some scientific terms. What I'm going to go over in this chapter is, what is a scientific theory? Is a scientific theory a fact? Can you prove a scientific theory? What is a hypothesis? How do you prove or support your hypothesis? And the scientific method. A scientific theory is an explanation of an aspect of the natural world and universe. In circumstances not amenable to experimental testing, theories are evaluated through principles of abductive reasoning. The meaning of the term scientific theory in science describes an explanation that has been tested and is widely accepted as valid. So not all theories can be tested, right? I posit that there's no way to test gravity, and many people agree with that, and many scientific sources agree with that. And a theory cannot be proven true. It's just widely accepted as valid, right? Some people, sometimes the scientific community gravitates to theories based on philosophical grounds. And I know that's kind of hard to swallow, but as we go further, maybe you'll start to see this point of view. Is a scientific theory a fact? A theory explains why or how. A fact is a simple, basic observation. A law is a statement, often a mathematical equation about a relationship between facts. Newton's law of gravity is a mathematical equation that can be used to predict the attraction between bodies. It is not a theory to explain how gravity works. Can you prove a scientific theory? A hypothesis is never proven correct, nor is the theory ever proven to be true. This is Jacqueline McLaughlin. She's a PhD associate professor of biology at Penn State. Here's the source. If someone tells you a scientific theory has been proven, you should ask what they mean by that. Normally they mean they've convinced themselves that this thing is true, or they have overwhelming evidence that a specific idea is valid over a specific range. But nothing in science can ever truly be proven. It's always subject to revision. That's Ethan Segal. He's also a PhD astrophysicist. This is from Forbes magazine. These are just two I grabbed. This is not something that's in contention in the scientific community. It's taught that you cannot prove a theory, right? No scientific theory can be proven. A scientific hypothesis is a tentative, testable explanation for a phenomenon in the natural world. It's the initial building block in the scientific method. Bear with me, I'm going to give you some examples of some hypotheses. For a solution to be termed a scientific hypothesis, it has to be an idea that it can be supported or refuted through carefully crafted experimentation or observation. This concept, called falsifiability and testability, was advanced in the mid-20th century by Austrian-British philosopher Karl Popper. And there's two terms that should pop out to you, which are interesting. Falsifiability and testability. So your hypothesis needs to be testable. It can't just be a claim. It has to be something you can test and control. And the outcome of it should be that you can falsify it through these experiments. If it doesn't have the ability, if your experiment doesn't have the ability to falsify your hypothesis, then it's bad science. A key function of a hypothesis is to derive predictions about the results of future experiments and then perform those experiments to see whether they support the predictions. A hypothesis is usually written in the form of an if-then statement, which gives a possibility and explains what may happen because of the possibility. The statement could also include may, according to California State University, Bakersfield. Again, my sources are always in here. Feel free to double check what you're getting here. How do you test a hypothesis? In hypothesis testing, we distinguish two types of variables, dependent and independent variables. The independent variable is whatever is presumed to bring about the supposed effect. It's the cause. The independent variable is the aspect that a researcher will manipulate in a study. The second type of variable is the dependent variable. The dependent variable is the variable for which we expect the supposed effect to take place. This means that the independent variable possibly caused an effect on the dependent variable, or it is presumed that the dependent variable's value depends on the independent variable's value. An independent variable is also called a factor or a predictor. So some examples of hypothesis statements. If garlic repels fleas, then a dog that is given garlic every day will not get fleas. So garlic would be the independent variable, and fleas would be the dependent variable. So as you manipulate the amount of garlic given to the dog, it should manipulate the amount of fleas you might see in the dog. If sugar causes cavities, then people who eat a lot of candy may be more prone to cavities. So candy would be the independent variable, and cavities would be the dependent variable. As you manipulate the amount of candy, we would see a fluctuation in the amount of cavities, right? And so on. I don't think we need to go through all these, but just want to make sure everyone understands the difference between an independent and dependent variable and how critical they are in a hypothesis. So the scientific method, all this in yellow, we've talked about it. This is just from another source. This is from Wikipedia, independent and dependent variables. But one of the things that's really a key factor when you're doing your testing is isolating effects, right? You can't prove something if without isolation. And what I mean is that if what you're trying to manipulate can be manipulated with multiple independent variables, you have to control those other independent variables. So if there's three factors that can manipulate your variable, your dependent variable, you have to track all of those. You have to take them all into account, and that's just called isolation of effects. So what are controls? Controls are the components and conditions that are known and kept constant during an experiment. Controls are used for a point of reference, and they are open safeguards against internal factors that may influence the outcome of an experiment. So these are referring to all your different factors, all your independent variables. That just kind of sums up what I just said and corroborates it. What happens if there are no controls in an experiment? And again, the search was, can you have an experiment with no independent variable? And the short answer to that is no. You can't have an experiment without an independent variable. It'd be meaningless. You have to, a proper hypothesis has to manipulate an independent variable and show causation on a dependent variable. I thought this was interesting. I didn't know exactly where to put it in the slide in my presentation, but Isaac Newton had no hypothesis for gravity. I wasn't aware of that. In his appended edition, the 1713 edition of the Principia, you'll find a phrase he used says hypothesis non fingo, which means I frame no hypothesis. So he had a formula, which was basically, it just calculated a mathematical rate of fall, but he had no hypothesis for what caused it. Feel free to search that for yourself and corroborate it. Does gravity have a hypothesis? So what is the hypothesis of gravity? If Newton didn't frame one, what is it? The general hypothesis is that gravity is an interior power of mass, and mass makes gravity. So this source is scitechnology.com, which science technology, I guess that's what it's short for. But this is the top result when I searched in Google. This is the first thing that comes up as of today, as of the release of this video. And what I thought was interesting is that the very first result says, be that as it may, nobody has ever genuinely comprehended this power, nor have they demonstrated its reality. It was talking about gravity. They haven't changed subjects. So they have never demonstrated its reality. So hypothesis, that almost says it's a weak theory, if you ask me. And we're going to hear more about that. This same phrase, this same paragraph has been used by multiple sources. This is Scholar Central, which I don't know why it references the Journal of Physics Research and Applications. Maybe that's where both of those sites got this. But this is the same statement, right? It says, from Newton to Einstein, we've accepted this hypothesis that gravity is an interior power of mass, i.e. mass makes gravity. Be that as may, nobody has ever genuinely comprehended this power, nor have they demonstrated its reality. So the hypothesis of gravity is that mass creates an attractive force. More specifically, the size of the attractive force is proportional to the masses of the objects and weakens as the distance between them increases. So enter the contrarians. Erik Verlinde. Erik Verlinde, if you're not familiar with him, is a well-known Dutch theoretical physicist. He's a professor of string theory at University of Amsterdam. He's been featured on many worldwide programs, such as The Big Think, which has, I don't know, millions of views. I can't remember off the top of my head. But he's been featured in every major science magazine. And he has some contradictions to what mainstream believes gravity is. So this is from one of the many articles on Erik Verlinde. He says, our current ideas about space, time, and gravity urgently need to be rethought. We have long known that Einstein's theory of gravity cannot work with quantum mechanics. So now you've got the scientific community divided, right? You have a lot of, if you're one of those people who subscribes to quantum mechanics, here's a physicist telling you I can only assume that we, the scientific community, have known that Einstein's theory of gravity cannot work with quantum mechanics. That's a concerning statement for someone researching gravity and whether it's a feasible theory. He goes on to say dark matter isn't the only gravitational inconsistency either. The standard model of physics, the best set of formulae we have to explain how the universe works, doesn't explain the effects of gravity. Interpret that how you want. He goes on to say, this is all from the same article, and this you can find this paraphrased and quoted identically in many sources. His suggestion is that gravity isn't a fundamental force of nature at all, but rather an emergent phenomenon. That term, you may not understand that. We're going to talk about that in a second. In other words, gravity is a side effect, not the cause of what's happening in the universe. So he's saying gravity is a side effect. That's kind of synonymous with an emergent phenomenon. At large scales, it seems gravity just doesn't behave the way Einstein's theory predicts. In other words, gravity doesn't work at large scales, which coincides with what you're going to hear from another physicist here in a minute, Walter Lewin. Remember this. So what does emergent mean, right? If something's an emergent phenomenon, in practically all scientific fields, philosophy, systems theory, science, art, emergence occurs when an entity is observed to have properties its parts do not have on their own. Properties or behaviors that emerge only when the parts interact in a wider hold. So that's interesting because the theory of gravity is that it's intrinsic to mass, right? It's not emergent, it's mass. It's intrinsic to mass. But this physics professor is saying it's an emergent phenomenon as a part of the whole system, which starts to sound a whole lot like luminiferous ether now. Now you've got this, at least to me, it starts to sound like another theory. Enter Walter Lewin. Walter Lewin is a Dutch astrophysicist. He's a professor of physics at MIT, also known as Massachusetts Institute of Technology, one of the most prestigious scientific institutions in the world. And we're going to let's hear what he has to say about electric force versus gravitational attraction.
And so you will easily be able to show that this ratio is roughly 10 to the 36. So the electric force is 36 orders of magnitude more potent than the gravitational attraction.
Okay, 36 orders of magnitude stronger than the gravitational attraction. That's the source. You can YouTube, just if you want to go to YouTube, search Walter Lewin 802.x lecture. Look for this pink shirt. And let's move on to what else he had to say. Now let's see what he says. What holds our world together?
So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces. that hold our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together.
That's a pretty point-blank statement, right? On a larger scale, planets, solar systems, galaxies, it's gravity that holds everything together. He said that up to thousands of kilometers, it's electrical forces. This is a guy he's an expert. He's an MIT professor of physics. This is what he knows. He just said, point blank, it's electrical forces that hold our world together. Gravity doesn't come into play until the planetary scale. Watch the whole lecture. Watch all his lectures. They're amazing. He's not the only person saying this. This isn't in contention. This is what he is teaching out of books. So, real world experiments and examples. I'm sure most of you have seen this. This guy's going to put an anvil in mercury, and I'm going to make a point with this in just a second. Is mercury anti-gravity fluid? Is that what we're to understand? This is a 110-pound anvil. You can find this video. He'll tell you. He said it's a 110-pound anvil. He can barely push it down into mercury. So where's gravity right now? Right? Obviously, the point I'm trying to make right now is that density in relationship to a medium, aka also known as density and buoyancy, is definitely a factor in what we consider gravity, right? Things going down. So in any experiment, you would have to take that into account. If your experiment's not taking density and buoyancy into account, it's bad science, right? So a little thought experiment, balloon world. What if we lived in a world where everything in that world was comprised of helium, right? People had helium bodies. We had little rubber suits like this yellow person. What if we were comprised of 99% helium, and trees were made of helium, and houses, everything? There would be no down, right? We would just float up to the sky, right? I know that's a silly thought, but it's something to think about. If you haven't thought about it, where's gravity then? If we lived in a world of helium-filled objects, where would gravity be? Is it an intrinsic down force now? Or is it more about density and buoyancy? Okay, well, that's certainly a factor. What about how do electrical forces? So here now we have another factor coming in, right? Do electrical forces affect weight? Well, let's see. Here we have something that looks heavy enough to lay down. It lays out on this table, right? So now granted, this is electrostatics we're looking at right now. And what effect does it have on this? So is this anti-gravity technology? Or are electrical forces a factor in things going up and down? I contend that electrical forces are a factor. Now let's look at, this comes from Good Times for All. If you're not familiar with Zachary Zabala, he does some great experiments.
Good Times for All, or Zachary Zabala here if you prefer.
And
in this video,
again, I really recommend you go into his video. I'm just going to summarize this because we had a lot of videos to go through, and I know nobody wants to watch a 1 hour video. But he's got this pen, a Karen B pen, and it's weighted. He made it, basically weighted it out so that it's hanging with using these balloons. It's hanging about 3 inches above the ground. He has this attached to a Van de Graaff generator, and when he adds a charge, he increases the charge to the pin. Watch what happens. It starts going down. And when he releases the charge to the pin, it starts going up. So I don't see how you could rationalize it any other way that he is affecting weight with electrical charges, right? And he discharges it and he recharges it and he discharges it and recharges it, and it goes up and down and up and down. And this thing was buoyant before he's messing with the Van de Graaff generator. It's just floating at 3 inches above the floor. And he sits there and shows you, look, I'm going to add a charge, it goes down. I'm going to release the charge, it goes up. Now he does an experiment with a gem scale, which is a very precise scale. And he's got a little Tesla coil here. And
Our electric field would like a
he's gonna take a 10-gram weight, and here's the weight. It's like right at 10 grams, almost exactly. And he's gonna power up this Tesla coil to change the electrical field around that weight. And let's see what happens. Does it change the weight? Oh, look at there. That's a very significant increase. Okay. Now I know what some people might think. You might say, well, it's somehow interfering. I mean, it's not breaking the electronic scale. It's changing the weight. But if you think that, later on, I've got an experiment that doesn't use an electronic scale. It uses a mechanical scale, and we do the same thing. Obviously, spring scales aren't as sensitive as like a gem scale, electronic scale. So we need a more powerful electrical source to manipulate it because we need a heavier weight. But let's see what happens when we see some of that. Again, good times for all. More of Zachary Zabala's experiments.
charge up an item.
And he's got the box that the scale goes in,
Static charge.
or that A scale goes in, and he's just
We have a piece of
he's got this
wire
lead
to a desk.
that he's got attached to the Van de Graaff generator,
It's
and he zeroes it out.
now
And let's
we
see,
see a big difference.
he zeroes it out.
Okay, so it's hanging around at 200s, 300s. I'm gonna get up. You'll see when I hit it. I'm gonna run a current to it. It's staying somewhat low right around there. I'll apply a current to it, and you can obviously see a big difference in the weight.
Now the squeaking you hear is he's turning. He has a Van de Graaff generator that you hand crank, but they're obviously not cheap devices. But you can see when he increases the charge on this lead here, and it's changing the magnetic field around this. It's gotten lighter. So are we to believe that electrical fields are anti-gravity technology? Well, they are. Let's look at this video from Munchausen today. And now he's got a spring-loaded scale. And he's going to put a device, he's going to put a 2 kilogram weight. Boom. 2.4 kilograms, 5 pounds. That's pretty heavy. And he puts this spinning contraption around it. It has magnets and mirrors. Okay, so that's like a half of a barbell right there. And this device isn't touching it at all. He goes on to show you later the insides of it. This is what it looks like. He just placed that around it, and when he placed it around it, it didn't affect the weight at all. He just placed it there. But what happens when he starts spinning it, right, and playing with this magnetic field? The water that so it dropped from 2.2 pounds to zero. It dropped to 2.2 pounds, less than half the weight. It was 5 pounds. There's an explanation for this. Something about reducing friction or something. He called it a heavy liquid. But go watch it. You can just go to YouTube at Munchausen today. It'll come up with this channel. You can find this very experiment. There are so many experiments. I couldn't put them all. We'd have a 4-hour video. Now let's talk about what I call anti-gravity vehicles. This company, Undefined Technologies, which you can YouTube, you can search for them at Undefined Technologies 6823. They created what you'd call a solid state drone. It has no moving parts. So they fly this drone around, and it doesn't have a blade. It doesn't have a propeller. The only thing it does is they use electrical charges on the wings, and they can fly this thing around like a regular drone. They call this ion thrust technology. They're saying that you're pushing down ions beneath it, but that's just a fancy redirect or misdirect from. It's really electrical forces at play here, whether they're electromagnetic or electrostatic. I'm not sure, but look into it, right? And we have some more videos. Here's just I think like a higher resolution video. You can hear it, kind of hear what it sounds like. Now you may think there's blades there, but there are no blades. There's no propellers. You can look this company up. They show it. They zoom in on it, and this is a solid state drum. There's no moving parts. These aren't exhaust. They're just little things it sits on. Now this is again. Here's the channel, Jim Rudgrogan 6610.
Anyway, today what I want to...
He's doing. I mean, he actually calls it, if I remember right, an anti-gravity experiment, because this thing, there's zero thrust. There is no thrust. Here you have it's a pretty heavy contraption, and it doesn't move this paper at all. Like when he has the paper laying under there, at some point he just has it laying under there. It doesn't. There's no movement on the paper, so there's no wind. It's not a. I don't think it's fair to call it ionic thrust, right? It's not. There's no thrust here. This is electromagnetic levitation. So this thing was on the ground, and he just cranked up the power on it. And there are many people. There's people that do this for science experiments, right? Here's a gentleman who has a completely different. Now he can't. This isn't sophisticated enough that he can redirect the electrical forces to the different quadrants to fly it, but he can.
Okay.
He does make it lift off the ground. And again, this is just, how's it flying? There's no wind. It doesn't have a propeller. He's doing this completely with electrical forces. So is electricity and anti-gravity? That's what you have to believe. Or is gravity actually a result of electrical forces? Again, I like this one. Here they are, and he's inside, and he's going to start testing it. And there's no wind whatsoever here. This thing just lifts up by manipulating. We have electrical forces. There's an electrical gradient in our atmosphere. It's 100 volts every meter you go up. Starting at the ground at 1 meter, it's 100 volts, and every meter you go up, it's an additional 100 volts. So that's proven. It's not up for contention. It's taught in science. You can research it for yourself. And our Earth is a ground. It's a negative. It's why we say that's how you ground things. So you have this downpouring of electricity that's just being poured out on the Earth, and the Earth is a ground. And you can manipulate these forces. And now, can electrical forces have an effect on water? They can. This is, again, Zachary Zabala with Good Times for All.
Hello, everybody out there in YouTube land.
And this is sitting on a Van de Graaff generator, and he just has a roll of tape here, and this is like a bowl or plate, and he has some water on it. And I don't know if you can see, the reason he has this dots behind here is so that he can capture the reflection of the water and show that the water is bending. And this water is bent. This is just a styrofoam ball that's painted with metallic paint. And he turns on the Van de Graaff generator, and it bends the water. So you absolutely can, and you can still see it. And now see the dots aren't bent at all. And when he turns on the Van de Graaff generator, you'll see. One second. There you go. So now the reason I showed this is, where have we seen this before? We have a pool of water, and now you can create ripples or waves in the water. It almost sounds like, if you have tides, might be being produced by electrical forces. Very, very possible. So what's an ion thruster? An ion thruster are categorized as either electrostatic or electromagnetic. Electrostatic thruster ions are accelerated by the Coulomb force along the electrical field direction. And by contrast, electromagnetic thruster ions are accelerated by the Lorentz force. So two different types, again, electrostatic and electromagnetic. These forces are both electrical forces. They're kind of categories of electrical forces. And just wanted to share that. Gravity fails when it should shine the most. If you're not familiar with the three-body problem, I've talked about this in a prior video called the macro and the micro. It has challenged people for centuries, and that's partly what makes it interesting. You're adding to the work of people like Newton and Poincare and Lagrange. Montgomery said, the fundamental problem is to predict the motions of three bodies, such as stars or planets, mutually attracted by gravity, given their initial positions and velocities. It turns out that a general solution to the problem is essentially impossible due to chaotic dynamics, which Henry Poincare discovered in 1890. I know I'm not pronouncing that right. I don't speak French. What they're saying here is that there's no solution to the three-body problem using Einstein's theory for relativity. The only thing you can, in his theory of gravity, the only thing that you can make work with a solar system is two bodies. The moment you go beyond two bodies, it falls apart. It becomes chaotic almost instantly. So I talk about this in great detail in the macro and the micro. You can kind of skip to that section. If you want to go reference it after this, you can go right to the section where I talk about the three-body problem. And I use explanations from PBS and other sources that really kind of make it indisputable that this is what they're saying here. So another source here, this is University of Oregon. The problem of determining the motion of three celestial bodies moving under no influence other than that of their mutual gravitation. No general solution is possible. So again, the moment you try to take, like for example, a solar system and you have the sun, if you have one planet or one body, you can make it work using Einstein's theories. But you can't do it the moment you add another body, a moon or a second planet, it falls apart, it breaks, right? There's no computer simulation that can take those equations and successfully have a solar system. The world's largest astronomy museum is inspired by classic three-body problems. So it's such a such a notorious problem that the largest astronomy museum in the world was inspired by it, right? So you'd have, I'm guessing these are the three bodies, but it's obviously a real thing. So two factors have been proven to play a role in what makes an object go up or down. Density and buoyancy determine whether an object goes up or down. Electromagnetic forces set the default direction, down, and play a role in the up or down. Nobody is arguing that things don't go down, right? We agree that. We agree things go down. Gravity is not a proven fact. A theory cannot be proven, right? You can't, for anyone that says, gravity is proven, it's not, right? It might be the consensus, but science will admit that you cannot prove it, right? Because you can only agree on it. But I've already shown you two physicists that have said very contradictory things about gravity. And Erik Verlinde, for one, seems to believe that gravity doesn't work. Right? The scientific community has known for a long time that Einstein's gravity cannot work with quantum mechanics. Apparently, this is widely known, according to Erik Verlinde. There is only evidence contrary to gravity. Example being the cosmological scale. So that where gravity should shine the most, right? Where it finally has the chance to overtake its counterpart, electrical forces, is on the planetary scale. But it doesn't work. It fails. Every solar system violates the mathematics that supposedly define gravity, right? That supposedly corroborate gravity. It fails. So the three-body problem absolutely contradicts the theory of gravity. The only place it works, again, it fails. There are alternative forces to gravity which can be verified. So why do you even need gravity? Why do you need mass has gravitational attraction? Gravitational attraction is intrinsic to mass. Why do you even need that? You can prove that electrical forces are pushing things down simply by manipulating the electrical force. If we know scientifically that there's an electrical force raining down on us, and I manipulate that that electrical force around an object, and I can make that object float, that's proven, right? That's scientifically proven. You have a hypothesis and you say that I believe that manipulating the electromagnetic field will affect an object's weight, right? And that's indisputably proven. You can also say the same thing about density and buoyancy. I believe that an object's density relative to the medium around it will affect whether it goes up or down. You can prove that. But where was gravity ever proven? How did any experiment ever manipulate mass? I've never seen an experiment. Feel free to correct me. That would be the experiment. Show me an experiment that takes account for density and buoyancy and takes account for electromagnetic and electrostatic charges, and it manipulates mass, right? I've never heard of that experiment, and that's why you saw earlier that the first result on Google and other scientific bodies stated it has never been proven, because gravity has never been proven. It's just a theory, and it's a lousy theory, and there's physicists that corroborate that, such as Erik Verlinde, and there's physicists that speak contradictory of gravity, such as Walter Lewin, who says the Earth at the atomic scale is held together by electrical forces, and electrical forces are 10 to the 36 times more powerful. So that's all I have to say. Hope you enjoyed the video. Until next time, take care.